So this is part 237, line 22b, Syngas fired coal, gas, hydrogen, electricity turbine. CO2 UFO 5G Wow Seti. So if we have the UFO 5G, obviously we have a formula in this video. Okay, so Wow Seti 1977 radio, that's your alien radio signal there. There's the equation and the answer to it. So Syngas fire turbine, NASA Google. So I Googled these keywords to find out what they mean. So this hot gas cleanup thing comes up here. Diagram. And it shows you a power transmission line, a transformer, steam turbine, product gas turbine. And it's got all these different little things with it. Okay, so this will be blogged on the blog, the Victoria Stafford of Psychic Investigation. I should be blogging them sometime this week, but I keep forgetting to do it because I'm doing a lot of weather predictions on there right now. We got 4 different hurricanes on the go. So, schematic diagram of possible CCS systems. So that's what that came up next. I don't know if you can see, it's kind of hard to read it. I can't read it and I got my glasses on, so it's just it's a nice little picture. Okay. So integrated gasification combined cycle IGCC. Okay, so we wanted to find out more about IGCC because that came up in the last video, right? Because if you are watching this video, you want to start with line 22A, okay? It goes from line 22A all the way to line 22E3, so there's a lot of videos. So how does integrated gasification combined cycle IGC work? Integrated gasification combined cycle IGCC is a combination of 2 leading technologies. The first technology is called coal gasification, which uses coal to create a clean burning gas, or syngas. The secondary technology is called combined cycle, which is the most efficient method of producing electricity commercially available today. Coal gasification, the gasification portion of the IGC plant, produces a clean coal gas, or syngas, which fuels the combustion turbine. Coal is combined with oxygen in the gasifier to produce the gaseous fuel, mainly hydrogen and carbon monoxide. The gas is then cleaned by a gas cleanup process. After cleaning, the coal gas is used in the combustion turbine to produce electricity. Combined cycle. This design consists of a combustion turbine generator, a heat recovery steam generator, and a steam turbine generator. The exhaust heat from the combustion turbine is recovered in the heat recovery steam generator to produce steam. The steam then passes through a steam turbine to power another generator, which produces more electricity. Combined cycle is more efficient than conventional power generating systems because it reuses waste heat to produce more electricity. The integration of these technologies provides the high efficiency of the combined cycle design with the low cost of coal for fuel. Higher output. Using syngas in a gas turbine increases its output, especially when nitrogen from an oxygen blown unit is fed to the turbine. Thus, a turbine rated at 170 MW when fired on natural gas can yield 190 MW or more on syngas. Furthermore, output is less dependent on ambient temperature than is the case with natural gas. Product flexibility, including carbon capture and hydrogen production. The gasification process in IGC enables the production of not only electricity, but a range of chemicals, byproducts for industrial use and transport fuels. See graphic. Carbon dioxide can be captured from the coal syngas. Carbon monoxide and hydrogen through a water-gas shift process. The CO2 can be captured in a concentrated stream, making it easier to convert into other products or to sequester, for example, store underground. See CO2 capture and storage. An added advantage in this process is that there are low additional costs for carbon capture, particularly if the plant is oxygen driven. In addition to electricity generation, hydrogen produced from the process can potentially be used as a transport fuel in fuel cells. So that's probably what we're going to use this for with this UFO design. That's what it's something to do with the hydrogen, and they use it in fuel cells. So you go www.globalgreenhousewarming.com. So the 30th of May 2012 is when I did the research on it. And of course I started in January, and now it's June 23rd when I'm actually filming it. My thoughts. I immediately think of the UFO engine here. We had another turbine invention come up earlier. I wonder if the two of them can be used. We use hydrogen in our jet propulsion fuel. You can use the exhaust heat from the combustion turbine to produce steam. Put it through a steam turbine to power another generator producing electricity. Low cost of coal for fuel. Why not use the formulas given for the fuel to make and try and see if it works with this system? And there it shows the temperature. Temperature contours: X to Z plane, Y equals 0. Combustion of methane in gas turbine can combustor. Z equals 134 millimeters. Just that little graph there. And this stuff here. And this one here. I'll just do a little quick pick here for you. Figure 4, temperature contours, XY plane, combustion of methane in gas turbine can combustor. Velocity W. There's that. Contours of the velocity W, Z direction in the YZ plane, combustion of methane in the gas turbine can combustor. Z equals 400 mm, velocity swirling strength. That's what that looks like. There's your numbers. Contours of velocity swirling strength XY plane, combustion of methane in gas turbine can combustor. This is the syngas H2CO 0.8. I guess this is what this is what all it makes. It all combines to this. Temperature contours for natural gas and syngas fuel mixtures with the same fuel mass flow rate affects the syngas composition as H2 and CO. And those are the two things that come up in the formulas. Hydrogen and carbon monoxide came up in some of the formulas, ideas that we came up with earlier. Table 2 is fuel and air injection conditions and power generated. I'm just going to show you this real quick here. Okay. Take a look there. Next is this graph here. And it's the fuel. Stuff there. Average carbon dioxide, CO2 mass fractions at the exit of can combustor, average mass of carbon dioxide at the exit per unit of energy generation. It's 10 times 10 to the 4, okay. So May 30th, 2012, there was lots more graphs in the diagrams above. I just pulled the ones from the beginning and end results. Please visit the site to see all the actual data processed. And next is advances in mechanical engineering. Combustion of syngas fuel and gas turbine can combustor. Chakuki Janai. He's from the Department of Ocean and Mechanical Engineering, College of Engineering and Computer Science from Florida Atlantic University. Academic editor is Hyung Yi-cho, and that's from 2010. So this is numerical investigation of the combustion of syngas fuel mixture and gas turbine can combustors presented in this paper. The objective is to understand the impact of the variability in the alternative fuel composition and heating value on combustion performance and emissions. The gas turbine can combustor is designed to burn the fuel efficiently, reduce the emissions, and lower the wall temperature. Syngas mixtures with different fuel compositions are produced through different coal and biomass gasification process technologies. The composition of the fuel burned in can combustor was changed from natural gas, methane, to syngas fuel, with hydrogen to carbon monoxide, H2CO, volume ratio ranging from 0.63 to 2.36. The mathematical models used for syngas fuel combustion consist of K to E model for turbulent flow, mixture fractions, PDF model for non-premix gas combustion, and P1 radiation model. The effect of syngas fuel composition and lower heating value on the flame shape, gas temperature, mass of carbon dioxide, CO2, and nitrogen oxides, NOx, per unit of energy generation is presented in this paper. The results obtained in this study show the change in gas turbine combustor performance with the same power generation when natural gas or methane fuel is replaced by syngas fuels. And these are the key points that stood out. Some sort of equation. Is the dependent variable that can represent the velocity UI, T the temperature, K the turbulent kinetic energy, E the dissipation rate of the turbulent kinetic energy, and F the mixture fraction. The governing equations are momentum equation, 2.5 mixture fraction F. In non-premix combustion, fuel and oxidizer enter the reaction zone in distinct streams. The equilibrium system consists of 13 species. Okay. The chemistry is assumed to be fast enough to achieve equilibrium. 5 syngas fuel mixtures with different fuel compositions. Low heating values of that were tested in this study. The results obtained in the study show the change in gas turbine combustor performance, temperature, flame shape, CO2 emissions, and no emissions when natural gas or methane fuel is replaced by syngas fuels with lower heating value and fuel compositions. And that's from www.hindawi.com. Blah blah blah. Okay? So the next video is going to be line 22C.